Welcome to The Explainer. Today, we're diving into a concept that's at the absolute core of every single large language model, the token. It's pretty much the language these incredibly powerful systems speak. You've probably seen some pretty staggering numbers thrown around about models with these massive context windows, right? Like 400,000 tokens. It's a huge number, and it tells you a lot about a model's memory and power. But what does that number actually mean? I mean, that number is the key to what a model can do. But the unit itself, it's a bit of a black box. Is it a word, a single character, or is it something else entirely? Well, today we're going to crack that box wide open. So here's how we're going to break it all down. We'll start big picture, then zoom in on the key piece of the puzzle, the tokenizer. After that, we'll get our hands dirty with the actual algorithm that makes it tick. And finally, we'll connect all the dots to see why this is so critical for how these models perform. Okay, so before we can really grasp what a context window is, we have to understand the unit it's measured in. You see, at its heart, an LLM is just a giant, complex mathematical function. It doesn't understand words or sentences or sarcasm. It only gets one thing: numbers. So the very first problem we have to solve is, how do we bridge the gap between our language and its? Well, we need a translator, and in the world of AI, we call that a tokenizer. You can think of it as this indispensable go-between that does two absolutely vital jobs: encoding our words into numbers for the model, and then decoding the model's numbers back into words for us. It's a really elegant three-step flow. You encode, you process, you decode. Simple, right? But this whole thing hinges on the tokenizer knowing how to break our text down into those numbers in the first place. And that leads us to how it's trained. So how does a tokenizer actually learn to do this translation? Well, it's not magic, and nobody's sitting there writing a bunch of rules by hand. It's a training process. And a really common algorithm, one used by big players like OpenAI and Anthropic, is called byte pair encoding, or BPE for short. The best way to think about BPE is as a form of data-driven text compression. It's all about efficiency. It chews through massive amounts of text, just looking for statistical patterns. Specifically, it's looking for which characters or little groups of characters just love to hang out together. The training process kicks off by building an initial dictionary or vocabulary from every single unique character in the training data. Each character becomes a basic token, and each one gets a unique number, its token ID. Now, this is a really important point. These IDs are just arbitrary labels in a lookup table. They have no semantic meaning by themselves. That's a whole separate step called creating embeddings, which happens later. Okay, now the clever part starts. The algorithm scans all of the training data and finds the most common pair of characters that appear right next to each other. So in our sample data, the characters Ji and Nung show up together more than any other pair. And once it's found that pair, two things happen. First, this new two-character token, Zhineng, gets added to our vocabulary with a brand new ID. And second, a merge rule is created. From now on, whenever the tokenizer sees zhi next to Nung, it's going to treat them as one single unit. Then it just repeats the process. The algorithm scans the text again, finds the next most frequent pair, in this case Ren and Gong, and merges them. The vocabulary gets a little bigger, and another merge rule gets added to the list. And this is where it gets really powerful, because the process is recursive. Tokens that were just created can themselves be combined to form even longer, more complex tokens. So here, our new Genkol and Jinan tokens get merged to form Renjikol Jinang, or artificial intelligence. This is how the tokenizer learns not just little character pairs, but entire words and even common phrases. So after repeating this merge process thousands of times, the training is done. Our tokenizer is now fully equipped with a huge vocabulary and a prioritized list of merge rules. So let's throw a sentence at it that it's never seen before and see what happens. Okay, so we start with our question. Does Mark like artificial intelligence? First, the tokenizer breaks the sentence down into its most basic parts, the individual characters. Then it starts applying its merge rules, one by one, in the exact same order they were learned during training. You can actually watch the process unfold here. It follows its priority list, first merging zhi and neng, then ren and gong. Then it sees those two new tokens together and merges them. And if we assume that Mark and Shihuan were also common pairs it learned, those rules get applied too. So after it's run through all its rules, our original 9 characters have been compressed into just 4 distinct tokens. And the very last step of encoding is really simple. It just takes each of those 4 final tokens and looks up their ID number in the big vocabulary table we built. This list of numbers, this is what actually gets sent to the language model to be processed. Decoding, as you can probably guess, is just that process in reverse. The model finishes its calculations and spits out a number, let's say 36. The tokenizer just finds that ID in its table, pulls out the corresponding text, Shihuan, and sends it back to us. And that's it. So let's circle all the way back to where we started with that giant 400,000 token context window. Now we can finally understand why that is not the same thing as 400,000 characters or 400,000 words. You see, the tokenizer doesn't just translate, it compresses. By smartly bundling common strings of characters into single tokens, it makes the input sequence for the model a whole lot shorter. This means the model has less to compute, which makes both training and inference way more efficient. So the most important thing to take away is this. Tokens are the fundamental unit of text for an LLM. They aren't a fixed size, but instead are variable length chunks of text that are totally defined by the statistical patterns in the data the tokenizer was trained on. And because of this, different models will tokenize the exact same sentence in slightly different ways. And now, that massive 400,000 token number makes a lot more practical sense. Since each token can represent multiple characters or even whole words, it lets the model hold and process way more information than if it was just working with individual characters. It's all thanks to this quiet, clever efficiency of tokenization. And all of this leaves us with a final, pretty interesting thought to chew on. If the entire system of tokens is learned from data, and different companies train their models on different data, what does that mean for how their models see and understand the exact same sentence? It's a fascinating question that gets right to the heart of how these things work. Thanks for joining this explainer.